divergence. So I just went over the flux form of greens right there. You take the force field and the dot product with n, that's the unit normal vector orthogonal to your curve, multiplied by arc length, which in differential form looks like that, m dy minus n dx, and you turn it into a double integral, and you got that divergence of f right there. Fine. So the analogous 3D version is called the divergence theorem. And it's going to give a relationship between a triple integral over a solid region Q and a surface integral over the surface of Q. Cool. And we did surface integrals on Monday, in case you forgot. All right. So in the statement of the theorem, the surface S is closed, and this is key. You cannot use the divergence theorem on surfaces that aren't closed. Just like you're not allowed to use greens unless the curve is closed. Otherwise, forget it. Go do something else. Go do the line integral by brute force, or if it's conservative, go use fundamental theorem of line integrals. Okay, so the surface is closed if it forms the complete boundary of the solid. That's how you know it's closed. Okay, fine. So what are some obvious closed surfaces? Well, spheres are closed. Cubes are closed. Tetrahedrons are closed. Parallelepipeds, which is a fancy word for a rectangular box, those are closed. So there's all kinds of solids, where the boundary, the surface is closed. Okay. So let's do the criteria that you need in order to be able to use divergence theorem. So the surface S must be closed. I just said that, but I'm going to say it again at the risk of being redundant. Fine. Then what? The Q must be a solid region whose surface is S, on which a triple integral can be evaluated. Otherwise, we're screwed because we're going to be doing triple integrals again today. Oh, I do not want to sign into Adobe. I don't know why it wants me to. Why does it want? No. One of my girlfriends, a colleague of mine, she texted me the other day. She goes, "Oh, my laptop died. I got to buy a new one. Do you have any advice for me?" And I said, "Yeah, don't get a Microsoft Surface Pro." Tell you what not to buy. It's my shameless plug against this horrible machine. And that the closed surface, write all this down, is oriented. Remember that? Remember oriented? Surface, we'll call this S, is oriented by outward, I'm going to underline outward, unit normal vectors. And I showed you this last time when we were doing flux integrals. So here's I'll draw some surface here. Maybe I'll draw an egg. It's got kind of so here's a region that's closed, but it's got two surfaces. It's got the upper surface, we'll call it S1, and the lower surface, we'll call it S2. And the upper surface, if you orient it with a bunch of cute little unit normal vectors that are kind of orthogonal, punching out like this, these are the little unit. The unit normal vectors kind of look like they're pointing upward. You want it to point out of the surface because you're going to submerge the solid in a jacuzzi or something, and you're going to basically, figure out some flux there. How much water is flowing across the boundary? Is there more water flowing out than in? And then if we orient the underside of this solid, the unit normal vectors are all punching more downward. So S1 is more oriented up, and the bottom surface we're calling S2 is oriented down. Okay, that's just a picture of how we're going. Okay, now you're ready. Let's do the divergence theorem. Woohoo! Folks, I'm so excited for you. Drum roll. We should have like a marching band come in right now. The fact that we even made it this far in the semester. Congratulations. Divergence theorem. Okay, criteria. You need a solid region bounded by a closed surface S, oriented by a unit normal vector, directed outward. So some of them might be up, some of them might be down, but they all have to be pointing out. And then if F is a vector field whose component functions have continuous partials on this lovely solid region Q, then here's what it allows you to do. If somebody says, go find the total flux, you could do the flux integrals that we did Monday, or you could do, and you might have to do more than one, because if there's different, different surfaces for your solid, like just as an example, how many surfaces does a cube have? Quick.
6.
6. There's 6 different surfaces. Really? Yeah, you got a top, you got a bottom, you got the front, you got the back, and then your right hand side, left hand side. So if you were going to do this surface integral that I just put up there, you in fact really would have to do 6 separate surface integrals and add the results. Yeah, I know. Big pain in the butt. But here's the cool thing about the divergence theorem. You only need one integral for the entire solid. And you do a triple integral though. So you got to be good at triple integrals. Remember that? Do you guys remember cylindrical and spherical coordinates?
It was merely 3 weeks ago. How
Yeah.
could I?
Did you always think, well, I hope I never see that crap again?
Nope, never thought that ever.
Yeah, well, good thing you didn't think that, because here it is. It's coming now to bite you in the rear end, okay?
I feel the same, George.
If you didn't get the cylindrical or spherical, hey, good news, you got a Thanksgiving weekend coming up. Make good use of it, people. Okay, so what is the divergence? Just a little review. You just took a quiz on it, but in case you forgot, for a 3D vector field here, it would be the partial of n with respect to x plus the partial of n with respect to y plus the partial of p with respect to z dv. Notice I use m's, n, and p's, and the book uses f's, g's, and h's. I really would appreciate it if you would use my notation on your handwritten work when you do your midterm and your final. I've been doing it enough in class. I would appreciate if you honor that. It's the more traditional notation anyway, and you'll thank me later. I know some of you don't listen to me though, but I'll just dock you a point or two for bad notation. I don't mind. You don't listen, you get docked. Okay, let's talk about what it means for divergence again. I alluded to this last Friday when we talked about divergence, but let's do it again. What the heck is divergence? It's the tendency for the field to flee from or diverge from that point. So if the magnitude of the vectors get larger as they pass through a point, the divergence at that point is positive, and that point is called a source. If, on the other hand, the magnitude of the vectors gets smaller and smaller and smaller as they pass through the point, the divergence of the vector field at that point is negative, and that point is called a sink. We'll talk more about sources and sinks in this section, okay? Because it's important. So here's a picture. So let's say you submerge this sphere into some vector field. I always like to think of the vector field as the velocity field of a jacuzzi water flowing around. If more of the water is flowing out of the boundary than flowing in, you could think, you call it a source, and that means your divergence is positive. But why is more flowing out than flowing in? And Dr. Vallone, my mentor, may he rest in peace, he used to say, well, if you can think of a little leprechaun in here, or a little gnome. He's a little gnome who's inside your sphere, and he's spouting water out to help the situation so that more water flows out than in. Now, on the other hand, what if more water is flowing into the surface than flowing out? That's called a sink. And you can think of your little gnome in here. Here's a little hat. The gnome is drinking water. He's sucking it down and then causing more water to be sucked in through the surface than out. So he's drinking it. Okay, and then you could have the amount of water flowing out equals the amount of water flowing in. They cancel each other, and you have your divergence is 0. And they have a word for that. They call it incompressible. Okay, fine. Let's do a somewhat easy example. I say somewhat easy. in this particular example, we aren't going to convert to cylindrical or spherical. We're going to stay in the rectangular coordinate system. No need to convert to spherical or cylindrical. And you have to know this. That's part of why you went through that last chapter, is to know the different, when should I stay in rectangular, or when do I need to start converting to an alternate coordinate system? That's for you to know. Okay, so this is not going to need any converting. So you'll see why in a moment. So let's the solid be a tetrahedron that's bounded by the coordinate planes, and the plane 2x plus 2y plus z equals 6. And I can easily graph this tetrahedron by, you guys know how to graph portions of planes. The z-intercept is 6, and then the x-intercept is 3, y-intercept 3. So I hope you can imagine the tetrahedron here in the first octant, bounded by the coordinate plane. So you got the base down here is like a triangle, and then you got the sides, and then you have this sort of slanted top, okay? And they want, if you did submerge this entire solid into the jacuzzi, what's the total flux through the solid? And then after we find the answer, we'll figure out, is it a source, sink, or neither? Okay, since the Q, the solid, is bounded by 4 surfaces, so I could say this, the total surface, if I had to, like if I had to do flux integrals and I wasn't allowed to use the divergence theorem, I'd have to do how many surface integrals or flux integrals? 4 total, because there's 4 surfaces that make up the tetrahedron. So that would be a real drag. So in other words, I would need 4 of these flux integrals. So 4 flux integrals, which look like this. We only did one example Monday, but you got to know how to do this for your midterm. Practice, practice, practice. It has this look. Okay, you have to do 4 different ones. One for S1, one for S2, one for S3, one for S4. Add up all the results, get the total flux. Okay, that would be painful. And we're going to do a little bit of pain today just so you can appreciate when we'll do a verify today. But if we apply the divergence theorem instead, which we're going to do, we only have to do one big old triple integral, and that's it. And we get the total flux without having to do separate integrals. Nice. So first, let's get the divergence of F, because we're going to need it to apply the divergence theorem. Surprise, surprise, surprise. So you guys know how to get divergence because that was on the quiz for Monday, and we did it last Friday. So if your vector field has components x, y squared, and z respectively, what is dm dx?
Just one.
1. Okay, somebody other than George, because I know he's awake, God bless. Who else could help me out here? What about the n there? There's n. What's the partial of y squared with respect to y? Say again?
2y.
Yes, thanks, Veronica. And then how about dp dz?
1.
1, yeah. So this is easy. It's just going to be 2y plus 2. Fantastic. So then what? So the total flux is going to be equal to this triple integral over the solid, 2y plus 2 dv, where dv represents the volume element. And the volume element for rectangular is what? What does that get converted to for rectangular?
Is dy dx.
Thank you. Yeah, that's my personal favorite order of integration too. So I'm going to have to, put limits on this triple integral. You guys know the deal. So put it in that order. And it might be good for us to figure out, since dy dx are the outer variables of integration. Let's take a look. Can anybody tell me what they think the region in the xy plane looks like here?
Line.
Yeah, well, you got a triangle because of the base of the solid. So if you set z equal to 0 in this plane equation, you'll get 2x plus 2y equals 6. And that's actually the line's equation. You get this right here. But if you solve it for y, which is pretty easy to do by subtracting 2x and then dividing both sides by 2, you should get 3 minus x. So that diagonal line is 3 minus x. So that's pretty easy to iterate your triple integral. X goes from 0 to 3, y goes from 0 to 3 minus x. But hey, what's z doing? You need to figure out the limits on that innermost integral.
Starts at 0.
Starts at 0 because the base is in the xy plane. And then what about how high it gets? Please don't say 6 because that's not correct.
I solved the plane equation.
Yeah,
for
you
Z.
want to solve the plane equation for z. Yes, very good, George. And then you would get 6 minus 2x minus 2y. So that'll be the upper limit for the z. Okay? And this is not too hard to do this triple integral. If you're integrating with respect to z, the 2y plus 2 just looks like a constant multiple. So I'm just going to sort of leave it aside and then just take my z and evaluate at the z limits. And that looks pretty easy, except for this is always ends up with some nasty algebra to do. Oh my goodness. You guys know you're going to have to distribute, distribute, and then also distribute. And so after I'll first distribute the 2y. Let's see, I'll get, what the heck will I get? What am I doing here? 2y times 6 is 12y. Oh, I see. My notes are kind of messed up. 12y, and then I have minus 4xy minus 4y squared. And then when I distribute the 2 times 6 is, oh, I see what I did, 12. And then 2 times negative 2x is negative 4x, and 2 times negative 2y is negative 4y. I always try to look for like terms. You guys see any like terms that we could maybe combine?
I think so.
What one
Yes.
is before?
I mean, you don't have to. You can just integrate right now with respect to y. But I'm noticing the 12y and the minus 4y, at least I could combine those guys into an 8y, right?
Mm-hmm.
Yeah, like I said, you don't have to. I mean, it's up to you how you want to roll. But if you do, you're going to integrate with respect to y here. It's like, oh, God. Yeah. And this is the part where, a lot of us blow it. And I do give partial credit. Like I give, even on the quiz you just took Monday, like if you were able to set up the double integral for greens with all the limits and all the stuff, I gave you like a lot of credit, like at least half credit. Even if my math lab gave you 0, I bumped up your points because it's like, hey, you set it up right, cool. And then maybe you bombed it after that. I can't help you there, but so then I'm going to have 4y squared minus 2xy squared minus 4/3 y cubed plus 12y minus 4xy. And I'm going to evaluate that between, oh no, 0 and 3 minus x. Are you kidding me? No, I'm not kidding you. Oh man, this sucks. So you're going to go, oh, do I really have to do this? And I'm just going to show you a little trick kind of to help a little bit. I mean, you don't have to use the trick. I think I went over something like this last time. You're going to have to kind of suck it up and do some of this distributing. And it's going to be a little bit of a nightmare, of course. But you could do a little bit of cleanup. So the cleanup that I'm talking about is, what am I talking about here? Let's see here. I had a whole bunch of 3 minus x terms. 12, 3 minus x. This is supposed to be a 3 minus x right here. Okay. So see these guys here. If you factor out a 3 minus x, then you get 12 minus 4x. But then if I factor out a 4 from the 12 minus 4x, don't I get 3 minus x?
Yes.
So those two together look like 4 times 3 minus x squared. Yeah, so what, So the point being is, like, if you try to combine all your 3 minus x squared terms, like see all those guys right there, you're like, oh yeah, does that help? It might. See what I have here. I don't know. I think I did multiply some stuff out, and then I tried to combine some of my 3 minus x cubed. Yeah, maybe not. Maybe that won't work. Yeah, you might have to FOIL it. Never mind. Okay. Sometimes you can get away with doing some stuff like that. And I think maybe in this one, I'm looking at my notes. It looks like I multiplied a whole bunch of stuff out. So after I multiplied everything out, I guess I didn't combine stuff. I ended up with this to integrate. I did use the power rule on at least this guy right here. So that guy I did keep out of the loop, and that way I could use the power rule on just that little term. And then the rest of these, I think just do them individually. Okay, I'm just going to put et cetera, et cetera. Whew. Final answer, 63 halves. That's the flux. Okay, so now I'm going to put it to you. Source, sink, or neither?
Source.
Source is correct
Source.
because it's positive. So that means you got a little gnome inside of your solid going, blowing liquid out. Okay. Not really, but you can think of it that way. Okay. So I'm going to do a verify right now, and it's not going to be fun. Anytime you see the word verify, that means verify. Do the left-hand side and the right-hand side. So what's the left-hand side and the right-hand side for the divergence theorem? So the divergence theorem's left-hand side, LHS for short, is a flux integral. And then the right-hand side is a triple integral, okay? So when you do a verify, please follow directions, because on your midterm, I'm asking you to verify agreements. So I want both left-hand side and right-hand side. So you're going to do a line integral, and then you'll do the double integral, make sure they're equal. Okay, so this is a paraboloid. I'll graph it. 4 minus x squared minus y squared, and it's bounded below by the xy plane. So it's got a flat bottom. So there's our solid. Fine. How many surfaces total does this solid have? Because that's going to give us information on doing the left-hand side. How many of those flux integrals do we need to do?
2.
2 is correct. You have the surface for the paraboloid, and then you have the base. So you have 2 surfaces. So what does this mean? You're going to have to first do the flux integral for S1, and you'll add that to the flux integral for the bottom plate, if you will, and that's going to give you total flux. That's the left-hand side. We're doing LHS right now. We're doing the verify, doing the LHS. And so I'm going to start with the bottom plate here by hand. So what is an obvious unitized normal vector that without having to do too much? I mean, the surface is z equals 0, certainly. But what is a 3-dimensional vector that is directed outward? And I'll give you a hint by drawing it. It's pointed downward, and it's only a unit long. What's an obvious one we can use?
0, 0, 1.
Close.
-1.
0, 0, -1.
Yeah, 0, 0, -1. Very good. That's going to be our unitized normal vector. Cool. And remember, when you do this f dot n ds, the n magnitude of the vector cancels with ds. You only really have to take the dot product of your force field with your normal vector that's not necessarily unitized. I mean, if it is, that's great. So this is what you're going to integrate over the region like this. And then your vector field is what? 2zxy squared. Now, normally when you do one of these flux integrals, because it's a double integral, every time I see the z, I blow a gasket, because you're supposed to replace the z with something involving x's and y's. So for this integral here, where the bottom is just this base plate, what's z doing in that xy plane?
0.
Very good. So this would be 0. So you could replace that with 0. Fine. Which doesn't really matter, because we're going to take a dot product, and that's 0 is going to multiply with this 0. Fine. And then you'll have, plus x times 0. That's another 0. And then you'll have y squared times -1. Fine. End up with negative y squared dA. I'm going to save this for later. I'm actually not going to finish this flux integral. You'll see why in a moment. I mean, I could. It's going to take me some time, but I'm just going to leave it for now. Okay.
Oh,
Don't worry, we're good. Now let's look at the other flux integral that I have to do. Am I bombing out?
Hello?
you're good.
I think
Am I still here? I'm having some wonky internet this morning. I don't know why. Let me know. Am I fading? Woo!
Very cool.
no, you're fine.
Oh my goodness.
So just to clarify really quick, well, that was all for surface 2.
Yeah, that was the bottom plate, S2.
All right.
We're going to do S1 now. S1 is sort of the lateral part of this paraboloid here, the other surface. I kind of saved it. So let's look at the S1 now. This is for S2 right here. So S1 is going to be what? You're going to go, okay, what's S1? F dot N ds. Okay. So you're going to have your vector field, and yes, I'll replace the z in a moment, but let me just copy down the vector field here. 2z, oops, copied it down wrong. X is the next component, and then the last component is y squared. Dot product with what? Now, folks, on your midterm and on your final, please don't blow this, because usually I make this worth a lot of points, and I get students who blow it because they don't look at the negatives. Have you ever blown a problem because of one little misplaced negative
Oh,
sign?
yeah.
Literally
what
did
I
it
mean?
last quiz.
Yeah, and one negative sign is going to just kill you, and especially in this class, as well as well, another place where it really kills you is differential equations. Anyway, I digress. Okay, so let me just repeat what I did Monday, because I know you probably forgot, or you're busy and you're too, you're getting ready for the Thanksgiving. You could care less. What you gotta, you gotta have here. You gotta have negative gx, negative gy 1. Do you remember this from Monday?
Yeah, that's
Okay.
a flux.
That is what you have to do now. So who's your little g? Your little g of xy is this surface here, the paraboloid, z. So what is the partial of 4 minus x squared minus y squared with respect to x? Somebody,
Negative 2x.
Very good. So watch closely with all these negatives. And if you can't keep your ducks in a row here, then maybe you should switch majors, okay? You're going to have minus, because this minus here, and then the actual partial is negative. Does that always happen? No. But in this case, it did. So, minus, minus, what does that turn into, people?
Positive 2x.
And then the negative gy, well, let's first get gy. What is the partial of 4 minus x squared minus y squared?
Negative 2y.
Y. So you're going to go negative, negative, and then the 1 just stays a 1. Fine. Okay. And then this part here, before you actually do the dot product, what are you going to replace the z with there?
4 minus x
4?
squared minus y squared.
Yeah, you got to put that paraboloid little g equation in there. 4 minus x squared minus y squared. And then the x just stays himself, and then the y squared just stays himself. Okay, now let's do some dot product. Okay, what's the verb for dot product? Dot producting? That's bad grammar, but what the heck? Let's actually do the dot product. So you got this guy times this guy. So 2 times positive 2x is 4x, and we'll worry about distributing that 4x later. And then multiply the 2 middle components together, fine. So we're going to add 2xy plus, and then you're going to multiply the last components together, fine. And this whole mass over the region. Now, I haven't said what the region is yet, because I've been kind of holding off. So what is this region and what is this region? And I claim for this particular problem, those are exactly the same, because the base of the solid is the region on which the paraboloid would have his double integral also. So if we examine that region R for both surfaces, it's going to be, if you set z equal to 0 with your paraboloid equation, and if you rearrange the paraboloid equation, ooh, don't I get a circle centered at the origin?
Yeah, radius too.
Radius 2. Fantastic. So that's the region for both. So why is that cool? Because I'm going to take this other surface integral, which I said, hey, let's save him for later. And I'm going to add him in the mix now because we essentially have to add these two integrals together anyway to get the total flux. And the reason why I'm doing this is because they both share the same region. You can put them in one big old surface integral, and you can't always do that for every single solid, but this one we can. And the reason why I wanted to do that is this y squared adds up with negative y squared. So what do they add up to?
0.
Yeah, that's kind of nice. Does that always happen? No, but I'm glad when it does. And so this is all I have to integrate. And then can you say convert to polar?
Arr.
Arr! Well, how come? Well, because the region's a circle. I mean, unless you like pain, come on. So you know the drill. This thing I would rewrite by pulling out a minus, and then that's an r squared, and then x is r cos theta, and this x is going to be r cos theta, and then this y will be r sine theta, and then r and theta, we got 0 to 2 pi for the theta limits, and then we have 0 to 2 for the r limits, and then we have this 4r cos multiplied by 4 minus r squared. I'm going to have to distribute this. Oh, God. And then when I multiply these guys together, I get 2r squared cos times sine. And then what am I going to have to replace the area element with?
Arr.
R dr d theta. And then, of course, you're going to want to distribute this r over the sum. And then you're going to integrate. And then, yes, you're going to have to use, you know, what are you going to have to use? This will probably take the power rule. And I don't know. It's going to take some time. I'm just going to put et cetera, because I'm tired. And I'm going to tell you the answer. Okay, the answer is 0. Cool beans. Yay. Aren't you glad I kind of just said I don't want to do that right now?
Absolutely not.
Aren't you tired? Okay, that was the left-hand side. So left-hand side complete, and the answer is 0. And that can happen. Your flux is 0. That just means the same amount of fluid flowing across the boundary out is getting canceled by the amount flowing in. Cool beans. Okay, now the right-hand side. I only have to do one big old triple integral for my total flux. I don't have to do multiple now. This is awesome. And I'll get the total flux in one shot. Beautiful. Fantastic. So then what? All right, well, what the heck is the divergence? I got to get that. You know, dm dx plus dn dy plus dp dz. What the heck? I don't know. I forgot what my force field was. Okay, so here's my force fields. Let's just do it up here. What's the divergence up here? Here's m. M is 2z. What's the partial of 2z with respect to x? Quick.
0.
Yay, plus. What's the
Plus
partial of
0.
x with respect
0.
to y? 0.
0.
Plus the partial of y squared with respect to z. 1 big 0. Woo!
That was
Baby. So
Sweet.
you're just going to integrate 0. And guess what? Surprise,
That's 0.
surprise, the answer is 0. And we win. Success. So which side do you like the best? The left-hand side or the right-hand side?
Wow.
The right-hand side.
I know it's tough. I'll let you think about it for a while. You know, don't be too hasty and rush into that decision. So is this a source, a sink, or neither?
Neither.
Neither. They call it incompressible. All right, whatever. Okay. Any questions so far on the divergence theorem? Aren't you excited?
It's really cool.
It's cool beans. So how about you guys try one? Are you ready?
Okay.
As always.
Okay, I want you to do example 4, and then I'll do example 3, 5, 6, and 7 to wrap it up today. Okay, I'm only going to give you 10 minutes though, so make it quick. I'm going to put you in a breakout room. So the one that I want you to do is not example 3, unless you're brave. Example 3, oh, hang on, I got a meme.
Good bean.
You guys should be laughing right now. Come on. That's funny, isn't it? Okay.
I'll take it.
Boy, you guys are You guys got to lighten up. Okay, I got another one for you. Studied everything except vector fields. 80% of the test was vector fields, Green's, Stokes, and divergence theorem, which all involve vector fields. Oops, should have studied the vector fields. Okay, example 3 is fine if you want to do that one. It's cylindrical coordinates. It's really cool beans. But here's what I want you and a buddy to do. So just give this a shot, and you don't have to do a verify, okay? Just use the divergence theorem only, okay? Only. That's it. Just use it, okay? Yes. Okay. Thanks, Sonny. Okay.
No.
Yeah, I'll say yes. Okay. My husband's trying to get me a book. Okay. Okay, I'll see you shortly. Good luck.
Is there anything important you gotta do?
I already know what to do.
Mike, man.
What are the other sides here? So x equals 1. If I asked you to graph x equals 1, would you be able to graph that plane?
X equals 1. Yeah.
What does it look like if I told you to graph it?
I mean, in 2D, it's a vertical line.
Yeah, but in 3D.
I mean, it has a vertical portion.
Yeah, well, it's going to be the plane that cuts through the 1 on the x-axis, and it's actually vertical, like it's flipped up on its side. You see how it's parallel to the YZ plane? Everybody? That's what x equals 1 would look like. Hello?
Yeah.
Now, maybe we should have another quiz on stuff from the beginning of the semester, because it seems to me like some of us don't remember how to graph planes. Because these are plane equations. Just because they only have one variable doesn't mean they're not a plane. I mean, you guys are probably used to seeing planes like, okay, 2x plus y plus 6z equals 12 or something like that. And that's a plane equation. But these are also plane equations, peeps. Okay, and y equals 2 would be a plane that cuts through the 2 on the y-axis. That would be parallel to the xz plane, like that. And then z equals 3 would be a plane that cuts through the 3 on the z-axis and would be parallel to the xy plane. So you should know these planes, because I'm going to put something like that on the midterm and the final. If you don't know it, you're screwed. So basically, this is a rectangular box, okay? Because it's bounded by the coordinate planes in these other 3 planes. So there's your box. So that's nice because it makes it easier when you set up the triple integral. So your total flux, which they always write with like a flux integral, like so, is really going to be the same as the triple integral over the solid, where we go get the divergence of the vector field. So if you did the divergence of this vector field correctly, you should have got -2 e to the negative xz plus 2xy plus 3z squared. Ooh, my goodness, that's a lot. That's your divergence. And then what? Well, my volume element, I'm going to do dz dy dx, just because that's my personal favorite. And then, you know, since we have a rectangular box, it's going to turn out that all the limits are constant. So z is just going to go from 0 up to 3, and y is going to go from 0 to 2, and x is going to go from 0 to 1. So this is pretty easy. If you integrate this with respect to z first, you should get negative e to the negative x z squared plus 2xyz plus z cubed, and you're going to evaluate that between 0 and 3. Now be careful, because, you know, some people got the wrong answer, because at the very end they forgot e to the 0 is not 0. Now here, when you plug in 3 everywhere, sorry, I got my meme already screwed up here. How did that happen? I don't know how it went all the way to the bottom. Okay. Well, that's my PDF annotate for you. I don't know what to do here. Try not to get it to be grouchy. So I'm going to get -9 e to the negative x plus, and then this is going to be 6xy plus 27. Okay, and that's pretty easy to integrate with respect to y. So you should get what? -9 e to the negative xy plus 3xy squared plus 27y after integrating with respect to y. And then you'll evaluate this guy between the limits of 0 and 2. And yet this time, yeah, the 0 goes to 0. So you're like, okay. So this is going to be, negative 18 e to the negative x plus 12x plus 27 times 2 is, I believe, is 54. Okay, fine. And now it's just a calculus 1 problem. And if you did this integration, you got positive 18 e to the negative x plus 6x squared plus 54x. And a big mistake people made because they kind of got used to, oh, don't worry about the 0. I won't plug that in because that's going to get everything 0, but not here. When you plug in the 1, you're going to get 18 e to the negative 1 plus 6 plus 54, which is 6 plus 54 is 60, minus, and then this term here, 18 e to the negative x. Be careful, when you plug in a 0 to him, he doesn't go to 0. So final answer, 18 e to the negative 1 plus 42, and it is a source. Okay? Any questions on that?
I got sort of confused about the parallelepiped because I remember we looked at one a couple months ago.
Mhm.
And the sides actually look like parallelograms, but this one is like a rectangular box.
Yeah, this one's more straight up and down. But it still can be called a parallelepiped. It's just one that's straight up and down.
All right. A fancy name for a box.
It's not like, because you can think of a rectangle as a parallelogram. It's a nice one.
That's math for you.
Yeah, that's math. Okay, I'm going to backtrack and let's go to the one right before it. This particular example comes from my high school calculus book from many years ago before you were born, but it's a really good one because you have to know cylindrical coordinates. And anytime you do a triple integral, you got to worry, should I stay in rectangular or do I need to convert? This one, you should convert unless you like pain. So cylindrical is the best choice. Well, how do you know that? Well, because the solid is this cylindrical surface. Remember how to get a cylindrical surface? You graph it in the XY plane and then you whoosh it in the direction of the missing variable. You guys remember whooshing? Hello?
Yep.
So this, after you put the generating curve here in the XY plane and you whoosh it in the direction of Z, parallel to the Z-axis, because that's the missing variable, you get a cylinder. But it's going to be bounded by the graphs of this can as well as Z equals 0. That's just the flat XY plane. You know, that's this flat plane here. And then Z equals 3 right there. So it's going to be a portion of a can. It's going to be only the can or cylinder between Z equals 0 and Z equals 3. Fine. So how many surfaces does this can have if I didn't know how to use the divergence theorem? How many?
3.
Yeah, you'd have to do 3 flux integrals, the top, the bottom, and then the lateral surface. And I don't feel like doing that. Forget that. Instead, I'm going to go, oh, joy. I'm going to just take that and do a big old triple integral instead. Fine. So, so let's get the divergence first, because that's always, you know, cool beans. So x cubed, the partial of that with respect to x, and then the partial of y cubed with respect to y, and then the partial of z cubed with respect to z, and I get that. Okay, fine. Now what? Well, this is where you decide what should I do. I mean, if you want to try and do this and rectangular, good luck with that. But the best choice is cylindrical because it is a candidate for cylindrical because the solid is a cylinder. So what are we going to do? dV is, that's the volume element, is going to get replaced with R dz dr d theta. And I hope it's obvious to you what the R and theta are going to be, because look, it's just going to be this circle of radius 2. So you've got R going from 0 to 2 and theta going from the whole circle around 0 to 2 pi. But what's Z doing? That's the innermost integral. What are you going to put on that?
Goes from 0 to 3.
Yeah, they told you it's just 0 to 3. Oh, that's nice. That was easy. And then what are you going to replace the integrand with? Well, the first two terms, if I factor out the 3, then the other factor is x squared plus y squared. I hope you can see that's r squared. And please remember that one thing that's beautiful about cylindrical, it's exactly like polar, where somebody just put a vertical z-axis on there and z just stays itself. Z is just z. Leave it. Now what? Well, they distribute the r over the sum before you integrate. And so I'm going to have 3r cubed plus 3rz squared. And I'll integrate with respect to z first. So I'll get 3r cubed z plus rz cubed. And I'm going to evaluate him between 0 and 3. And I think I'm going to get 9r cubed plus 27r. And this is super easy, people. No power reduction formula or anything like that. Integrate with respect to r, I get 9/4 r to the 4th plus 27/2 r squared. Okay, fine. And then evaluate that between 0 and 2. And I think I get 90. Ooh, that's beautiful. And then the last integral is just a 1 with respect to theta. And I think you go, hey, that's just going to be theta, go from 0 to 2 pi. Final answer, 180 pi. And that's a positive number. So it's a source. So there was an example of triple integrals where it was really helpful to convert to cylindrical coordinates. That's good to know. And then what do you really think that's cylindrical? I know a lot of people hate. What do they hate? Spherical. So we're going to do one with spherical. Yeah, because we can. And while I'm teaching you this lovely topic, I want you to notice this weird notation here. This is taken from a vector calculus book. It's not weird notation. It's how the vector calculus people and even the physics folks denote a flux integral. Well, how come they don't have a double integral? Because the flux integral is supposed to be a double-double. Well, they know it's double because they're lazy, because they put an S down here. So it's sort of understood that you know, because you're in the mystical brotherhood of mathematics, you know that that's really a double integral. And not only that, the circle means closed surface, just like the circle meant a closed curve when we were learning greens, same kind of thing. And then the n is a lowercase, and you'll see a little subscript out. That means outward directed a vector. So you'll see that a lot of times. So I just want you to notice that. I'm just trying to enlighten you with other notation for your future. Okay, so what do we know? We know that the total flux through the solid, which happens to be a sphere centered at the origin of radius 2, and here's the vector field. It's going to be found by doing the divergence theorem, because we love the divergence theorem. And we'll go like that. Okay, fine. So what is the divergence? Okay, if you look at your vector field, the partial of 2x cubed with respect to x. Oh, stop. Don't buy a Microsoft Surface Pro, people. 6x squared, partial with respect to y, 6y squared, partial with respect to z, 6z squared. And then you've got this going on. And you're like, oh my God, well, the solid is a sphere. So guess what? Convert to spherical. So on the entire sphere, what are r and theta and phi? Phi looks like this. What are all of those doing? So let's just do that. Rho, theta, and phi. Rho is doing what?
0 to 2.
0 to 2. Theta is doing what on that full sphere?
0 to 2 pi.
Mm-hmm. And phi is doing what on the entire sphere?
0 to pi.
If I were asking you to do this with a hemisphere, that's half a sphere. Hemisphere, half the sphere. What would rho be for a hemisphere? I just want to go over this because everybody should know how to do everything.
What would be
rho? Would be the same. Rho don't change.
Okay.
What would your theta be if you were doing a hemisphere? Like
it doesn't change.
Doesn't change. What would phi do if I had the upper hemisphere?
Pi halves.
Pi halves. Very good. Okay, now let's do it one more time. Suppose I said I only wanted the first octant portion of a sphere. So here in the first octant, you would only take, you chop that little piece off your sphere, the first octant portion. What would rho be?
Same.
Same. What would theta be?
Pi halves.
Pi halves. What would phi be?
Pi halves as well.
Also pi halves. Good. You
got this, Nick.
Nick, you're going. So I just want you to have, those are usually your 3 candidates when you're doing spherical. Okay. So I'm going to convert to spherical. So what I'm going to do is I'm going to pull out the 6 from the x squared, y squared, z squared. Why am I doing that? Because that gets replaced with what?
Rho squared.
Mm-hmm. And what is the volume element for spherical? Let's see how well you remember from the midterm a couple
Rho
weeks.
squared sine phi. D rho, d phi, d theta.
Yeah, I say phi, but you can say phi if you want. Okay, so then you want to, of course, combine your powers of rho into one big old rho, which would be 6 rho to the 4th. And I think we mentioned that we're going to go 0 to 2, 0 to 2 pi. Oh, no, 0 to pi. Sorry, my phi is middle. And my theta, I usually save my theta for last, just personal preference. And if you did this integral, I'm just going to keep going here. I'll do it. What the heck? I think a lot of us need some review on spherical because that was a big bomb for the midterm, unfortunately. I'm going to put the 6 and the sine phi next to each other. When we integrate with respect to rho, we're going to get what? 6/5 rho to the 5th going from 0 to 2. And we still have to integrate with respect to phi and theta. Wait, why do I have 2 6s here? Sorry. I already put my 6 over here. Let's just put 1/5. And then when I evaluate 1/5 rho to the 5th, between 0 and 2, I should get 32/5. I'm going to pull out the 6 and the 32/5. They're bothering me. And then I just have to worry about sine phi. What is the integral of sine phi?
Minus cosine.
Yeah, minus cos. And we're going between 0 and pi. So you're going to get minus cos pi minus a minus cos 0. There's a lot of minuses floating around. Don't blow this. So this is minus minus 1 plus 1. 1 plus 1 is 2.
I'm leaving. Could you check my dad from time to time?
Yes.
Okay, good.
Yeah, I will. So that's a 2, and then you don't have to worry about that because that's constant multiple. And then finally, when you integrate with respect to theta, you get theta going from 0 to 2 pi. So your final answer is something weird, 768 pi fifths, and that is a source. Okay, and we're done with that one where we had to do spherical coordinates. Know how to do spherical. Okay, any questions so far? Let me pause the. Okay.
Cooking for tomorrow?
Yeah,
Yeah, I know how that
we
goes.
got my father-in-law down here, and yeah, he's 95. Yeah, okay. So now look at example 6. You're going to have example 6. I'm telling you, you should know this, okay? Know this for the midterm, know it in your physics class. I imagine it's going to be on a physics midterm if you take physics, because it's really a cool problem. It looks really hard. It's like, I can't do that. It's like, yeah, you can, and it's cool. So there's this vector field that's given by the curl of some other vector field. Those kinds of vector fields are kind of special. Vector fields that are the curl of another field. They're called solenoidal fields. Okay, we're going to show that the total flux of this vector field is solenoidal. It doesn't matter what the surface is. If it's, as long as it's closed, the answer is going to be 0 regardless. What? Yeah. So let me use that weird notation just to be weird. So you're going to go, okay, this F dot N out ds, that's total flux. That is going, I'm going to use some more weird notation. Instead of doing a triple integral, watch this, people. I'm going to do one integral, just one, with a circle around it and a V down below. That means it's a triple integral. Ha ha! I don't make this stuff up. I just report it. And you'll do the divergence and then dv. Okay, fine. So what's the divergence? They didn't give me enough information. That wasn't very nice. And they didn't tell me what the vector field was. They just go, oh, it's going to be a curl of somebody else. And then we're not even going to tell you who the somebody else is either. Ha ha! Yeah, you're like, okay, not enough info. I can't do the problem. Yes, you can, because I taught you how to do this. You're going to take the divergence of F, but F is given by the curl of some other vector field, and then you're going to cite the Biggie theorem. And you had to cite a Biggie theorem on your last quiz. I think the last problem was a multiple choice and the answer was 0. And all you had to do, some of you like reproved it. Thanks for the tip, but no need. You just had to say, by the Biggie theorem, I'm done. The divergence of the curl is, it's basically, go look at your Biggie theorem and when we did divergence and curl in 17.5. The divergence of curl is 0. And so what we can say is that anytime we do one of these divergence of F for this particular vector field, not for everything, it will be 0 no matter what the closed surface is, every closed surface, which is kind of cool. Okay, and now I'm going to finish today with a very cool problem, my homage to Dr. Arnie Vallone, and he did this problem when I took him for vector calculus a few years ago. And it's kind of a cool trick that is just awesome. And I hope that after you see it, you'll think it is as awesome as I thought it was when he did it. Okay, so check it out. What if somebody said to you, oh, I need you to find the flux through a surface that is not closed? Okay, and the surface that's not closed is the northern hemisphere, that's the upper sphere, of a circle of radius A, and let's say it's centered at the origin for ease. So if you can imagine this upper hemisphere, not the bottom plate, it's not closed. You're only wanting to find the flux through this open surface. Okay, and here's the vector field. Well, that's going to be kind of hard, and I don't feel like doing it because then you're going to have to convert. And, I actually even tried doing this by hand, and it was like, oh my God, what a nightmare. So I was like, okay, now I see why he did the trick. Okay, so here's the plan. Instead of finding what we want, and what we want is find the flux through that not closed surface, we're going to do a little trick. We're going to close off the surface. So we'll give it a base, the base plate down there, just that flat base, which is a circle. We're going to close it off. Now it's a closed surface. Ha, ha. And then we're going to use the divergence theorem and find the total flux over this closed surface. And then we'll subtract the bottom flux, which is just the base plate. So I'll write down what we're doing here, okay? So we're going to do, here's the goal we want. We want the flux through the northern hemisphere. That's what we wish we can have, but it's kind of a challenge to get it. It's a real pain. So what we're going to do is we're going to get, we're going to look at the closed surface and get that flux. And then we'll subtract off the base plate flux. Like this. This is the plan. This is the strategy, okay? So this is what this over here is what we want, but it's kind of a hassle to get. And these are kind of easy. This one, I can use the divergence theorem, which is cool. And then this one, I'm going to use an actual flux integral. That's an S, sorry, for just the bottom base plate. And then I'll have my answer, okay? So we're going to do this in pieces. So let's do the closed surface flux first. So you're going to take the northern hemisphere and give it a base, and now it's a closed surface. So what are you going to do? So you're going to go, okay, I want the divergence of F, and I'm going to go like this. And let's see. Oh, I don't know what just happened because I always lean on my surface and it goes somewhere else. Okay. So what are we going to do here? Well, what is the divergence of F? Okay, well, let's see. dm dx is 1 plus dn dy is 1 plus dp dz is 1. Oh, man, that's awesome. It's just a 3. Okay, cool. I'm just going to pull the 3 out of the triple integral. And now looky here. I could convert to spherical because, the hemisphere is a spherical candidate, but I'm going to jump ship here. And I put a couple of problems like this on your quiz in 2D that you just took from me Monday. I don't know, some of you noticed it right away. Good for you. Where you noticed, hey, this either the dn dx minus dm dy was a constant or the divergence was a constant. And you're like, hey, but that's just multiplied by the area of a circle. I'm not even going to bother doing that double integral. It's just representing area. Hey, we're done. And that was exactly what you're supposed to do. Cool beans. You'll do that a lot in physics too. And that's why I'm training you for that. So this is going to happen in physics. You're like, this represents the volume of the hemisphere. So you're going to use the volume of the sphere and just take half. What do you mean? Well, the volume of a whole sphere is 4/3 pi r cubed. Okay, so half of that is a half 4/3 pi r cubed. Okay, so that looks like it's going to be 2/3 pi r cubed, and the radius for ours was like some constant a. So we get that. Okay, so hold on a second. Just trying to see what am I doing here? Why did I get 2 pi a cubed? Hold on a second. Let me just pause this for a moment. Okay, so then when you get your total flux, 3 times the volume of half a sphere, the 3's cancel, and you get 2 pi a cubed. Okay, save that for later. Save that for later. So in my little box diagram, this box, we just got his flux, and it's 2 pi a cubed for this particular example. So I'm just going to put that up here, store that up here, 2 pi a cubed. Okay, fine. Now what? We're going to subtract off the base plate flux. Well, what the heck is the base plate flux? Well, what's an obvious, since we're going to do one of these, we're going to take a dot product. What is an obvious unit normal vector that is orthogonal to that flat surface?
0, 0, -1.
Yeah, we did something like this today. Exactly right. So that's going to be your n. Because z is just equal to 0, so 0, 0, -1 is your normal vector. And then what is your vector fields? You've got x, comma, y, comma, z plus 1, like this. Oops, now you're converting it to a regular integral, so I'll just put r here and then dA. Now, you're not allowed to have 3 variables in a double integral. Like, that's not good, and count on that happening in your midterm, and you're going to do something about it because I taught you what to do. You have to replace the z with something because I only want to see x's and y's in a double integral. What are you going to replace z with? Well, what's z doing in the xy plane on that base plate?
0.
Z is 0. Bingo. So that's just going to be a big old 0 right there, 0. And now take the dot product. Okay, fine. X times 0 is 0 plus y times 0 is 0. Plus 1 times -1 is -1. Okay, so it doesn't go to 0. Okay, it's -1. Then what? I'm going to pull the -1 out. And what do you guys know about a double integral that just has a 1 as its integrand? What does it represent?
It represents region.
Area of the region. And what is the region? It happens to be a circle, right?
2 pi r.
Yeah, it's centered at.
Or 2 pi
Careful, careful. You're doing circumference.
a.
I want area, pi r squared.
Uh,
And so the r for us is a because we were just using this generic circle of radius a. So you're going to go, okay, -1 times pi times a squared. Okay, so the flux through the bottom base plate is negative pi a squared. What does the negative mean?
that there's, I don't know how to phrase this. Sorry.
Well, you know how we were computing the outward flux because we got an outwardly directed unit normal vector, you know, that's directed down, but it's out of the base plate?
Yes.
Since we got a negative number, it means the water is actually going, or whatever electromagnetic field or whatever, it's going in the reverse direction. That's all. Okay, so fine. So now we're ready because this over here was negative pi a squared. So what is the total flux? This is what we want. It's 2 pi a cubed minus a minus pi a squared. So the final answer, folks, is 2 pi a cubed minus minus turns into a plus pi a squared. And that is the final answer. And that's definitely a source because that is going to end up being some positive number for some positive radius. And we're done. Okay, so what I love about this problem, just to recap, is the trick was, hey, I don't feel like finding the flux through that surface. It's going to be too hard. So you close it off, make it closed, and then compute the total closed surface flux using the divergence theorem. And then you just subtract off that little base plate flux by doing a little mini flux integral. That's not too hard. because 0, 0, -1 was the normal vector, and it wasn't hard to integrate. In fact, we didn't even integrate. We just, had an area. And, and then there you go. So is kind of a fun problem. Now, I'm not going to put there's nothing like this on the homework. There's nothing like this on the midterm. There's nothing like this on the final. Okay, I promise. There's no trick. So please, even though I just showed you this really cool beans example, this was partly for me because I have to enjoy myself sometimes when I'm doing this class. And I love that problem, and Arnie, my mentor, he was great. He taught it to us. So don't be doing this trick on any of the homework or exam problems. Okay, you don't need to. I just wanted to show it to you. Okay, so any questions on this?
When you were finding the base plate flux, would greens have worked on that or no?
Well, greens would not work because greens is through a curve only. You're computing outward flux through a curve. And here we want the flux to the whole surface.
Oh, I see. Okay.
Yeah, there's a little different flavor to Green's flux thingy. Yes, it's 2D, but you're thinking of it through a curve, like outward flux that's going in or out of the curve, not through the actual base plate itself. Does that make sense?
Yes.
So you're going to have to do the flux integral from the previous section, 17.6. Sorry. Okay, any other questions? Everybody good? And I'm gonna stop the recording, but I'll